In this video, we're going to look at the applications of quadratics. So we'll start off by looking at a bit of the theory and an introduction to applying quadratics to different situations, and then we'll move on to two examples that mainly focus on area. Quadratic equations can be applied to many practical situations, including flight paths of projectiles, such as balls or even things like javelins or shuttlecocks, or the area of rectangles and triangles, and that's where we're going to focus our two examples on today, or buildings such as arches and bridges, and finally resistors in electrical circuits even rely on a quadratic relationship. So when you're applying quadratics to different problems, you may need to do some or all of the following. So you might need to define a variable to represent a quantity in a problem or question, such as let x be the length of something in the situation you're dealing with. You may then need to determine a quadratic equation that relates quantities together, and we will be doing that in both of the examples. You may need to substitute values into an equation and or solve equations to find answers to problems. And you may need to choose solutions that are reasonable given the context of a problem. So for example, we know that things like length must be greater than 0. So when we're talking about reasonable or practical values for a situation, we're actually talking about a thing called the domain of a rule. So domains might restrict the values that go into the rule to be between a lower and an upper bound. And we're actually going to explore that in one of the problems. Finally, you might need to find a maximum or a minimum value for a quadratic relationship. And that obviously relates to the turning point of a graph. So now let's get into some examples. So our first example includes a right angled triangle that has an area of 25 meters squared. And we can see that one of the lengths is x minus 1 and the other length is x plus 4. And for part A, we're asked to determine the value of x. So first of all, we know that the area of a triangle is given by the base times the height over 2, and that's going to equal the area. So therefore, for this question, the base length is x plus 4, and the height is x subtract 1, and we divide that by 2, and that's an expression involving x that now captures the area. And for this question, the area is 25 meters squared. So that means we can substitute that in for A. So now we just need to solve this quadratic. So we're going to end up with x plus 4 multiplied by x subtract 1 is equal to. And to get rid of that divide by 2, we multiply both sides by 2. So that makes this equal to 50. And then we can expand this bracket. And we'll just go over here and use a grid to do that. So up the top we might have x subtract 1, and down the side you might have x plus 4. And expanding we would get x squared minus x plus 4x minus 4 as the expanded values. And we can see that the 4x and the negative x are like terms, so they will combine. So overall we'll have x squared, and then it will be positive 3x minus 4 is equal to 50. And we know whenever we solve a quadratic, we always want to get it equal to 0. So to do that, we're going to subtract 50 from both sides of the equation. So that means x squared plus 3x minus 54 is equal to 0. So up next, when we solve this, we can factorize and use the Null Factor Law. And we're going to look for factors of 54 that add up to positive 3. So if we just list the factors of 54 to start with, we could have 1 and 54, we could have 2 and 27, and we could have 3 and 18. 4 and 5 are not factors, but 6 is, so we could have 6 and 9. And now one of these pairs, it turns out, does multiply to negative 54 and add to negative 3, and that is if we have negative 6 plus 9. So using these two values, we can factorize. So we can turn this into x plus 9 multiplied by x minus 6 is equal to 0. So therefore, our null factor law says that x plus 9 could equal 0. Or we could have x minus 6 is equal to 0. And that would give us x is equal to minus 9 or x is equal to positive 6 as possible values for this. However, x is a length. Therefore, we know that x must be greater than 0. So that's what we might call a domain restriction, or just a practical or reasonable test for this case. We need the lengths to be positive. So in particular, because we have an x minus 1 here, more than x being greater than 0, we actually need x to be greater than 1 for this case. So that means that x equals 6 is the only solution that we want for x for this problem. For part B, it says, hence determine the perimeter of the triangle. So we now have the length of the base and the height of the triangle, and we now need to find the hypotenuse because it's a right-angled triangle. So we know that c squared, the hypotenuse, is equal to a squared plus b squared, where this length of x subtract 1 is now going to equal 6 subtract 1 equals 5. And the x plus 4, if I just trace that out in orange, is going to equal 6 plus 4 is 10. So the hypotenuse, if I put that in red, is c for this formula. So therefore we have c squared is equal to 5 squared plus 10 squared. So therefore c squared is equal to 25 plus 100. So therefore c is equal to the square root of 125. So we continue along and we get c is equal to the square root of 25 times the square root of 5. So we can simplify that surd by identifying 25 as a perfect square. So that gives c, the hypotenuse, as being equal to 5 times the square root of 5. So this c value up here, we can now write as 5 times the square root of 5. So the perimeter, which is what we were asked to find, is going to equal the height of the triangle 5, and then we add on to that the base of the triangle, which is 10, and then we add on the hypotenuse, which is 5 times the square root of 5. So the perimeter is equal to 5 plus 10 is 15, plus the hypotenuse, which is not a like term to the 15, so they have to remain separate, and that is the perimeter. And because the perimeter was in meters squared, we know that this must be a length in meters. So that's the answer to example 1b. For example 2, we have a farmer decides to enclose a paddock using 60 meters of fencing. The paddock borders a straight river, meaning that only 3 sides of the paddock require fencing. The diagram provided shows the design of the paddock and the river. So for part A, we need to show that the area of the paddock is given by the rule a equals negative 2x squared plus 60. So to start off with here, we need to think about what information we're given. And we know that we have a total of 60 meters of fencing available, and it's going to be split between this side length of x, a second side length of x, and then a third side length of length y. So there is a way to relate that information. We know that the length of the fence is equal to x plus y, and we know that that's also equal to 60 meters because that's how much fencing he has available. So therefore we can say that 2x plus y must equal 60. So we now have a relationship between x and y related by the fact that we know there's 60 meters of fencing. However, we want the area of the paddock. So we want the area, which we know is equal to x times y. However, we don't want x and y to both appear in the area expression. So we're going to come up to the equation that we just had before, and we're going to get y by itself. So that means that y must equal, and to get y by itself, we're going to subtract 2x from both sides of this equation. So y is going to equal 60 minus 2x. So now wherever there's a y here, we can replace it by 60 minus 2x. So therefore the area is going to equal x times 60 minus 2x. And then if we expand that, we get that the area is equal to, and this would be 60x minus 2x squared, which we could write in the order minus 2x squared plus 60x. So that is the rule for the area of this paddock in terms of only x, which we were asked to show back up here. For part B, we're asked to sketch the graph of a equals negative 2x squared plus 60x. So to graph this quadratic, we're going to find the key features of the graph. So we're going to start off with the y-intercept, or technically it's the a-intercept, and that occurs when x equals 0. So therefore we'll have a is equal to minus 2 times 0 squared plus 60 times 0. So we just get that a equals 0. Then we can move on to finding the x-intercepts of the graph, and that occurs when y equals 0, or technically when a equals 0 for this example. So that means we'll have the equation 0 equals, and it's going to be in factorized form will help us to solve this equation. So we can remove minus 2x as a highest common factor. So we're going to have minus 2x times x minus 30. And just take a moment to hopefully agree with me that that's the factorized expression. And that means we can use the Null Factor Law, which says minus 2x could equal 0, or that x minus 30 could equal 0. So therefore we just have x equals 0 for the first equation. And then for the second option, x take 30 equals 0. When we add 30 to both sides, we get x equals positive 30 as the second x-intercept of the graph. Finally, we're going to find the turning point, and I'm going to use the fact that it occurs halfway between the x-intercepts of the graph. So therefore, the midpoint between 0 and 30 is simply going to be found by doing 0 plus 30 over 2. So we know that x equals 15 gives the maximum or minimum turning point, but it is going to be a maximum turning point. So therefore the area when x is 15 is going to be minus 2 times 15 squared plus 60 times 15. So we just substitute 15 into our rule. So therefore the area is equal to minus 2 times 15 squared, which is 225, plus, and 60 times 15 gives 900. So therefore the area is going to equal minus 450 plus 900. So the maximum area, or the turning point, has a y value of 450. So that means the coordinate is going to be 15, 450. So now that we've got the y or the a intercept, both of the x-intercepts of 0 and 30, as well as the coordinate of the turning point, we're now well and truly ready to sketch this graph. So just before we jump into sketching this graph, I'll just draw your attention to the negative, or the negative 2 that's out the front of the x squared term, which means that the parabola is this shape, it's concave down. So plotting the points we know that this is going to be 0, 0, and this point here is going to be 30, 0, and halfway in between we have 15, 450 as being the turning point. And now joining all of those points with a parabola shape, we'll get this as our graph. So this point here was 0, 0, this point here was 30, 0, so they were the two x-intercepts and it doubled up as the y-intercept. And the maximum point was 15, 450. So that's the answer to part B for this example. Next up, part C asks us to state the values for x which have meaning for this question. And in brackets, it just says that this is actually referring to what we'd call in maths a practical domain. So what values of x make the rule have meaning for a practical situation like this? So things that we might like to think about is that the length must be greater than 0, and for a practical situation, the area must be greater than 0. And that also applies to situations that might involve time or that might involve volume as well. So anything that you measure, we consider it must be greater than 0. So if we highlight the part of the graph that satisfies that x is greater than 0, the length, and the area is greater than 0, then we just have the part that's shaded there. And if we were to describe that yellow highlighted region in terms of x, so this is what we consider a domain, we'd start here at x equals 0 and would continue until x equals 30. So therefore the domain which is what we call this practical set of values for x, would be x is greater than 0 but less than 30. So that is the answer to part C of this question. Next, we're asked to determine the area of the paddock when x equals 5. So on the graph, which has been computer generated for this slide, so it's just trimmed down to that domain we were just talking about, x equals 5 might be around here. We want to find what the y value is, and that represents the area that we are being asked to find. So to do that, we're going to use our rule, and that says that the area is equal to minus 2 times x squared. But the x value has been given to us as 5, so it's minus 2 times 5 squared. And then it's plus 60 times x, so it's plus 60 times 5. So therefore the area is equal to minus 2 times, and that's 25, so that's 5 squared is 25, so all up we'd have minus 50, plus 60 times 5, which equals 300. So therefore the area when x is 5 is equal to 250 meters squared. So that is the answer to part D of this question. So just over on the graph, we know that that area is 250 when x is 5. So the last part of this question is simply to state the maximum possible area for this paddock. And we already found that when we graphed this rule, because we found that when x is 15, we had a maximum value of 450. So the area that is a maximum is simply equal to 450 meters squared. So that is the answer to part E of this question. So after this video, you should be able to define a variable that represents a quantity presented in a question or problem, to be able to determine a quadratic equation that represents a relationship within a question. You should be able to graph a quadratic relationship and identify any practical restrictions to a rule or graph. You should be able to substitute values into and or solve a quadratic equation. And finally, you should be able to find a maximum or minimum value for a quadratic relationship.